Okay, so in the last video I talked about what a polar bond is. In this video I'm going to talk about a polar and a nonpolar molecule. Okay, so this is on page 134 of your notes, and there's also a handout that was not in your notes that you would either get a hard copy of, or I'm going to upload it to Blackboard as well, so you have that for these notes. So it's all fun to talk about if a bond is polar or nonpolar, but most of the time we have multiple bonds inside of a molecule, so we need to talk about whether a molecule is going to be polar or nonpolar, okay? So a polar molecule is just basically talking about one end of the molecule, just like the bond, is going to be slightly negative and the other end is going to be slightly positive, okay? If a molecule has a slightly negative and a slightly positive, we say that it has two poles, which we call a dipole in chemistry, okay? So what does that mean? That means if I was to place a polar molecule between like a magnet, the positive side of that molecule will orient itself to the negative side of the magnet, where the negative side of the molecule will orient itself to the positive side of the magnet, right? And I'm going to show you an example using water here. So for example, water is a polar molecule, okay? I know this because the bond between hydrogen and oxygen is polar, okay? If I was to do that math, the difference between those two, I think it's like 1.2 or something like that. Let's see, 3.5 and 2.1, so the difference is, it's actually 1.4 is the difference in electronegativity. Okay, so what this means is this side of the molecule is going to be partially negative, where each hydrogen is going to be partially positive. Okay, so what this indicates is if I was to place a magnet here, the negative side of the molecule will be attracted to the positive, where the positive side would be attracted to the negative. Okay, and water is really special in this case because what happens when I have multiple water molecules together is the water molecules kind of orient itself like this, where this partially negative oxygen is really interested in being close to the positive, partially positive side of another water molecule, okay? And this is why we get a lot of different things like surface tension. And you've probably done this experiment before where you drop water onto a penny and it kind of does like this bubbling over type effect where it doesn't spill. And that's because water has this special tendency to be attracted to each of the molecules inside of water, okay? So how do I tell whether a molecule is going to be polar or nonpolar? We can kind of use a flowchart, okay? Because now we're not just going to talk about whether the molecule bond is polar or nonpolar. I also have to talk about whether the bonds kind of cancel each other out. And we'll talk a little bit about that here in a second. So a polar bond is an unequal sharing of electrons, which we talked about before, where a nonpolar bond is equal sharing between two atoms, okay? So a polar molecule is going to have a region in a three-dimensional type of space, think of our ball and stick models, with a partial negative and a partial positive, where a nonpolar molecule is going to have no region of charges at all, okay? So not only does it depend on the bond polarity, but it also depends on the symmetry of the molecule. Okay, so the first question you need to ask yourself, are the bonds nonpolar? If the answer is yes, that's easy because the molecule is going to be nonpolar. Okay, if the answer is no, we need to ask ourselves one more question. Does the molecule have symmetry? If the answer is yes, it's going to be a nonpolar molecule because the bonds will cancel each other out. If the answer is no, it's going to be a polar molecule. Okay, so let's look at a couple of examples here. First one, let's talk about the electronegativity difference between the bond of carbon and oxygen. Okay, so let's look at the electronegativity difference between carbon and oxygen, okay? So if I look at my periodic table, carbon's electronegativity is 2.5 and oxygen's is 3.5. Okay, so the difference is 1.0. So the type of bond between carbon and oxygen is going to be polar. Okay, so the question states, Are the bonds nonpolar? The answer here is no. So now I have to draw the molecule to figure out whether it's symmetrical or not. So if I was to draw carbon dioxide, it looks like this. Know how to draw carbon dioxide. Hint, okay? So the shape of this guy, it's linear, right? Because there's no lone pairs on the central atom. Therefore, this is a linear shape. Does this molecule look symmetrical? The answer is yes. If I was to look at this in a three-dimensional aspect, meaning if I was to cut this guy in half, both ways, so this way and this way, the molecule is symmetrical, okay? So since the molecule is symmetrical, we're going to say that this is going to be a nonpolar molecule. And I'm running off of here. So I just wrote nonpolar molecule, meaning there is going to be no charges on this species, meaning there's no partial negative, there's no partial positive, okay? Everybody wants the electrons equally, and that's what a nonpolar molecule means. Let's do another example, water. So the difference between, so my bond in water is H to O, and hydrogen is 2.1, oxygen is 3.5, so the difference is 1.4, which makes this a polar molecule, an extremely polar bond. I'm sorry, polar bond, an extremely polar bond, because that difference is pretty large. The Lewis structure for water, know how to draw water's Lewis structure, okay? The shape of it is bent, okay? So you need to remember that water had this bent-like structure because of those two lone pairs of electrons that take up space and push down the hydrogens on either side of the oxygen. So with that being said, this guy in three-dimensional space, it's symmetrical this way, but what really messes it up is the fact that it's three-dimensional, right? Because this is not going to be equal to the top. The top is not going to be equal to the bottom. Therefore, this is not a symmetrical molecule. Therefore, this is going to be a polar molecule, okay? This region of the molecule will become partially negative, where this region of the molecule is going to become partially positive, okay? I'm going to do one more. H2S. H2S looks very similar to H2O, so I want you to do that one by yourself. Let's do NH3. So we're doing nitrogen to hydrogen. Nitrogen is 3.0. Nitrogen is 2.1. The difference is 0.9. The types of bonds are polar. Okay, if I was to draw this, the structure would look like this. Okay, so this nitrogen has two electrons that are taking up space. Therefore, this is going to be my trigonal pyramidal structure. Okay, is this symmetrical? No, because it's going to look like that little, it's going to look like a pyramid almost. Okay, so the top definitely doesn't look like the bottom. So we're going to say no, and this is going to be a polar molecule. Okay? So that means that since nitrogen has the higher electronegativity, this portion of the molecule is going to be negative, where each hydrogen is going to be positively charged, or partially positively charged. Okay? I'm going to do one more. If you were to do something like Br2, I hope in your head you're thinking that this is going to be a nonpolar molecule because the bonds are nonpolar. And your answer to that would be yes. So that's it with polar versus nonpolar molecules. Thanks for watching.